Further functions. By now, we should have already seen how basic functions work. We know that functions can take arguments or parameters and give us some returned value back. We also know how to define our own functions, what parameters we want them to take, and how we get them to return values. These are actually all the fundamentals we need to know, but that doesn't mean there's no more to talk about. In this session, we'll be looking at some of the more advanced use cases and features of functions, as well as some of the handy tricks that Python has built in to help make working with functions a little bit easier. Keyword arguments. Remember from last time that we define function parameters in the brackets around our function signature. We said we had to give them unique and valid names. Here's an example of a function which takes 3 arguments. This function takes a username, a first name, and a last name. Then it checks to see if that username has already been taken. If it hasn't, the new user's details are stored in the dictionary accounts, with the username as the key, and the function returns true, as in yes, executed successfully. If the username has already been taken, the function exits early and returns false, as in no, something went wrong. So far, so good. But it's not very flexible. It can only take 3 arguments. It can't take less, it can't take more, always 3. Maybe that's not so much of a problem now, but what if we wanted to extend this to take extra optional details like phone number or email address, or if we wanted the option to override existing usernames some, but not all of the time? Well, we could just define multiple functions, and this would work for sure, and in some cases that's enough. But all of those functions would have to have different names, you'd need to implement them all separately, and remember which one was which when you needed them. You might end up with register, register and override, register with phone, register with email, register with phone and email, register and override with phone and email. You see, it gets pretty overwhelming pretty fast. In Python, there is a way to make functions more flexible, so that a function can be programmed to do 2 or more different things depending on what and how many arguments it's given. Keyword arguments, sometimes called quargs as opposed to args arguments, are arguments that may or may not be included in a function call. And if they're not, they default back to some given value, typically some empty or failsafe value. We write them as so. They are written the same as regular arguments, but with an equals and a default value. We can have as many keyword arguments as we want, and we can even include both regular arguments and keyword arguments. Although if we do this, all non-keyword arguments must come first. Let's apply this to our register example, starting with phone number and email. Here we've given both new parameters default values of NA, as in not applicable. You'll now see that we can call this function with or without these last 2 arguments. But what if we wanted to include email and not phone number? Surely that's impossible because the email parameter has to come after the phone number. Well, actually no. This is one of the good things about keyword arguments. You can write them out of order, so long as you explicitly state which one is which by name in the function call. This is why they're called keyword arguments. A common use for keyword arguments is to add extra options for functions, sometimes in the form of booleans. Let's give the option to override existing usernames. Internal functions. We know that we can call functions inside other functions. You can also define functions inside functions. They're called internal or nested functions. These can be super useful if you're doing something relatively complex multiple times inside your function. The same reason we'd use functions anywhere else, really. Keep in mind, though, that an inner function won't be usable anywhere else outside of its outer function. However, nested functions can be very useful and good for organization, just so long as you're absolutely sure you're not going to need them anywhere else. Introducing recursion. By now, you might have thought to ask yourself, hang on, if we can call one function from inside a function, can we call one function from inside of itself? And yes, you can. This is called recursion, and it opens up a whole world of exciting possibilities as well as things that could potentially go wrong, which can be super useful. It's something that really deserves its own session, but for now, we're going to briefly go over it. Take a look at this example. Maybe you think this is just like an infinite while loop, and will keep running quite happily forever. Unfortunately, it's not so simple. Say we call our function foo for the first time. It increases I, and then calls foo again. Remember that the first function call hasn't stopped yet, and it won't stop. Not until the new foo function it calls stops. And of course, that one won't stop until it calls another foo, which will then call another one, and another, and another, and another, and so on, all piled on top of each other. Unlike loop iterations, function calls need to be kept active in memory until they terminate. For this example, none of these function calls ever stop, ever return, because they're all waiting for the one above them to stop. Eventually, we are going to run out of space. What happens then, usually, is that the program environment sees what's happening, calls it a stack overflow, a special kind of error, and brings the whole thing to a stop. Sometimes this doesn't happen in time, and the operating system has to step in, freezing or terminating the program. If you're very, very, very unlucky, your entire computer might start to slow down or even crash altogether. Don't panic. Modern systems are very unlikely to just let this happen, but still, much better to be careful. This has all been a lot of doom and gloom. Does this mean recursion is just stupid and dangerous and we should never use it? Actually, no. We just need to make sure that the call stack doesn't just keep growing forever. We do this by introducing something called a base case, a case in which a recursive call is not made and the process can return. Take a look. All we've done here is introduce a statement that will return out of the function once I reaches 5. Let's walk through it in action. The first time we call foo, we pass it a value of I equals 1. This then increases it to 2, checks to see if it's greater than or equal to 5, which of course it's not, so it calls foo again with I equals 2. This call then does the same thing, increasing I to 3, and checking before making a new call, and so on and so on and so on, until finally a call is made in which I equals 4. This last call increases I to 5, which means that the condition is met, and the function call gets to terminate without making another call. It returns 5. You see that this return value then gets returned all the way down the call stack until the call at the bottom, the original one we started with, finally terminates. We're done, and we get our final value, 5. This is a classic example of base and recursive case functionality, where the call stack only grows as high as it needs to. That is, it keeps growing until some condition, the base case, is met, and the whole stack sort of collapses back in on itself, passing down any return value from the top with it. Type hints. Finally, a brief word on how different data types are used in functions in Python. Say we write a Python function which is meant to take a number, divide it by 2, and return it. How could we know that when baz gets called, x will be a number that we can divide, and not some other data type, like a dictionary or a string, that we can't divide? This is tricky because Python follows a philosophy called dynamic typing, where the type of objects, like variables and parameters, don't need to be explicitly labeled in the code itself. Python is just happy to wait until the program is actually running and just trust everything as the data type it's meant to be. But if it isn't the right data type, say we call baz with a boolean, then this is obviously a problem. We can't divide a boolean. Luckily, there is something we can do to prevent this. We can introduce type hints for our parameters. See how after parameter x, we've added a colon, plus the name of the type we're expecting. So what does this actually do? The short answer is nothing. They're really only there for you and anyone else you're sharing the code with. The longer answer is technically nothing. The Python runtime environment, that is the thing that actually makes your code go at the very core, completely ignores them. But depending on what extra tools you're using, such as your editor, these type hints can be picked up on, and used to automatically check for potential mistakes or inconsistencies in the code. If one such mistake is flagged up, your editor may alert you to it, a bit like a spelling mistake in a word processor. Some extra tools may also stop the program running before any inconsistencies are resolved. You can also use type hints for variables and the return type of functions, although the syntax is slightly different. We use this funny arrow written with a dash and a triangle bracket. Remember, type hints are actually completely optional. They change nothing at the very lowest level, but they're favored by a lot of people. It can just make your code feel neater if you know what every type is meant to be. Summary. With these, we've covered everything we need to know about functions. You'll be seeing these a lot throughout your coding career. You'll be writing your own functions, of course, but you'll also be using ones that have been written by other people. Having a solid understanding of Python functions, both how they work inside and how they're used, is essential.